All right. Good morning, everybody. We're about to start. So if you're here, please turn on your cameras. And, okay. All right. So this is going to be the last day of a lecture or like a regular lecture. So we're going to wrap up the content on experiments. And I'm also going to talk a little bit about statistics to clarify something that I think needs further elaboration. And so let's get to be started, actually. And so we talked about many challenges that experimenters face when they trying to conduct experimental research that are related to how we make sure the experiments are valid, or like they actually make sense in representing what they claim to represent in the theory, but they represent it well when they conduct the experimentation itself. So in terms of the materials people are going to experiment and the way people or participants in this case could answer, right? And so we mentioned things about the validity of measurement, the validity of stimuli, but there are also other things related to the context. And one important one is something called ecological validity, right? And ecological validity simply means that the extent to which the conditions of in a lab experiment reflect the situation in real life. Okay, to the extent that whatever we found in an experiment could be applicable to real life situations. Okay, and you can think about like in different sorts of cases, right? So if I bring you in to play a video game in a lab setting, right? And so they would be like one person, let's say the main researcher, me, right? And I'll hand you different devices and I'll be sitting at some corner and I will invite you to, okay, go and play this game. And maybe I'm having even more like sophisticated stuff. So I have like, have you seen, maybe you've seen this device, like the electromagnetic um, devices that you wear on your skull. And so it could detect when your brain fires up electricity, right? So that's an experimentation method, but the idea that would that affect that, how does that affect the nature of how you play video games, right? Because that situation of playing video game is different than when you play video games just in your normal life. And so that setting presumably would affect how you react to materials, the amount of attention you're going to pay, the like maybe the different strategies you're going to take. Your whole mood is different, you know? And so the idea is if you're doing experimentation, how you make sure that the lab environment is similar to the normal environment. And that's even, by the way, I'm not talking about lab in necessarily in a physical sense. So even if you're conducting an online experiment, so you would obviously have more ecological validity, but it could be different. So suppose, for instance, that you're doing experiments on advertising, and so the commercial you're testing is supposed to be aired on TV. but people watch it on their mobile phones because they're conducting an online experiment. So that those two, those two contexts are different. So they might get different results, right? One example also, think about if you're doing experiment on dating and dating strategies. So like, what are like the dating strategy under stress? Or like, if you're interested on what type of like, what they call like self-disclosure or like uncertainty reduction strategies. So uncertainty reduction, by the way, so in personal relationship, in romantic relationship in particular, you don't know who the potential partner is, right? You just someone you just saw online or offline. So you're uncertain, like, okay, is it like safe to go with them? What's their situation? Are they single or not? They're interested or not? So like there's something called uncertainty reduction, which is like you ask about the name, where do you work, blah, 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 where do you go to school, those type of things, like those type of questions. So imagine doing something like that. You're studying dating, but then you're inviting participants who are single, like inviting into a room and like large dining room, and you tell them, okay, imagine you're trying to approach that someone to ask them out. What would you do? And it's sort of awkward to do that in an experimental setting, and you're being watched, and there are other people, and so you are actually wanting to say that this experiment results would reflect what happens in the real world. But the more you are getting into something that is different than what happened in the real world, the validity of your results would be lowered, right? So you want to have something as close as possible to the real life experience, which can hardly be achieved 100%, but at least researchers need to try to make it happen. I'll give you a very simple example, like something from research that I've conducted. So imagine like if you're studying Instagram, if you're doing some Instagram research, and if you want to study the effect of like a fashion blogger on purchase intention or whatnot. So there are things you could do, right? One thing that you could find researchers doing is that because I am studying the effect of a fashion influencer or blogger, then I'm going to show you Instagram posts from that account that are all about product endorsement, like all of them, okay? Where in reality, we know, for instance, that Instagram influencers and other accounts have a variety of things, right? Some of them would be related to product promotion, some of them would be not. And so something that I would do, or I did do actually, is with that, you include some elements that are not related to your hypothesis. So you could see here, I had like 6 images or posts, and some of them are like just here, like just a scene, like a palm tree and a beach. And then there's another one here, like there's like sea waves. And so I included content that make that Instagram account look more authentic. And I made that page like interactive, so people could actually click on each image and then they can press like or dislike. So it feels like, so although they were not on Instagram itself, it felt like Instagram. So I got the experimental experience as close as I could to the real life experience. And that's something, by the way, for your, speaking of which, the final project. So if you're proposing any experiments, make sure, yeah, that at least the materials you try or the things you show, or like the setting you're suggesting, is as close as possible. And again, it's as possible to the real life experience, okay? So that's about ecological validity. So those are considered the challenges. Now, that leads us to talk about something related, which is the external validity of experiments. The external validity is to remind you that the findings of the research could be generalized or applied to the outside world, right? And so we say like there are two types of generalizability. You have population generalizability and you have theoretical or analytic generalizability. And since we know that it's really hard, as we established like in a few lectures ago, that it's really hard to use a real random sample. So to remind you, random sample means that each member of the population has an equal chance of being included, which could really hard. If you think of it, it's almost impossible to have. If you're doing an experiment on the US population, it's really hard to have everyone, to get everyone an equal chance to be included. So you would rely on some sub-sample frames. You do via a marketing firm. If you have money, like there's like some market research that could get participants, but it's still not fully random. So the issue is here is that the aim of experiments is actually not to establish sample to population generalizability. Okay, and this is a key difference between experiments and surveys. If you remember the example, like if you're doing survey and I want to know which candidate is going to win the election in one state, the whole point of doing that public opinion survey is that the percentage of my survey would reflect the percentages in the real world, right? However, in experiments, we're actually not interested in that. We're interested to see if the two variables you're testing are indeed related. And so what you're trying to generalize to is like generalization from the context and the study you have, the experiment you conducted, to the theory that you claim explain and or predict human behavior. Okay, so the generalizability is about the effects of X on Y and not about the population percentages. And let me give you an example so things don't stay like in the abstract realm. So suppose, here's an example. So suppose you're doing a research and you're saying you want to see how hunger affect how people respond to food advertisement, okay? So hunger affecting food advertisement. Your hypothesis is, let me get a pen right here. So people who are more hungry will respond positively, more positively to advertisement about taste as compared to advertisement about nutritional value. All right. So that point, is that clear, like what the hypothesis is trying to say? So if you're hungry and then you see advertisement about food, you would respond more positively to the one that is emphasizing taste as opposed to the one emphasizing the nutritional value or the health benefit, something like that. And the logic of it is some sort of somewhat intuitive, like so hunger activate the food craving parts of your brain, like you want a good taste. And so when you're hungry, you would respond then better to taste-centered messages, right? You're hungry, you start thinking about sugary stuff and salty stuff and fatty stuff and all that, all those type of things, right? And so those part of your brain, if you're thinking like more on physical terms, those parts of your brain will be more active than things about, oh, how would that be beneficial to me, or how this meal is going to be healthy, right? So a message that center the taste of the meal would be more appealing to you if you're hungry, okay? Right here, this is the independent variable, as you can see. So in terms of generalization, this is really important. Regardless of what the majority prefer, what we want to generalize is that hunger affects human choices in terms of like food. But make of equals more when taste than nutritional value. So assuming we found this is true, okay? So people in the hunger condition, so hunger condition, so it's like hypothesis one, people in the hunger condition responded better to taste messages than nutrition messages, right? we can generalize that people in general, in the real world, when they're hungry, they would look for taste appealing meals, right? Regardless of what happens under normal circumstances. And this is what we mean by we're not interested into sample populations. So, for example, so if the majority actually preferred nutrition-centered messages, right? If the majority in our sample preferred nutrition-centered messages, yet we saw that the condition with hunger made people like taste better or taste messages better. That's actually the thing we want to demonstrate, right? So we're not interested to say like, okay, so the majority of the sample, 60% like nutritional messages and 40% like taste messages. That's not the point of experiments. The point of experiment is say, okay, under no hunger, so under the control condition, 20% like taste messages and 80% like nutrition, for example. But under hunger, that 20% increased to 30% that prefer taste and 70% that prefer nutrition. So you see, it's still a minority, but compared to the control, it actually increased. Hence, we say if this situation occurs or appears in the real world, we should see a similar effect. That hunger would lead to like more emphasis on taste. Okay, so that's what we mean, right? And so that's what experiments are for. So experiment control for the issue about sample to population generalizability, because we have random assignment to groups. And so you are actually trying to generalize about connections of one variable to the other, and not about what the majority or the minority of the population think or do. Okay. And so that's actually it about experiments. To summarize like why we do experiments. So the most important things, by the way, and I asked about this last time, experimental research are fundamental to establish causal relationship, right? So causality are established in experiments on only via experiments, and except under like very extreme exceptions. But causality, to say X causes Y, can only be established via experiments because you can control for alternative variables or alternative explanation. That's the most important things to remember. Then in terms of experimentation itself, the key, there are like two things. First is that the validity of manipulation. So to remind you the example we gave last time. So you're saying humorous commercials are more effective than non-humorous commercials, okay? And in order to do that, you have to establish first that the materials that you are using in the experiment are actually humorous. In the condition you say it's about more humorous, and less humorous in the condition that you say are less humorous, right? So before we get into like the effects, you actually need to establish that the message attributes represent the independent variable you're trying to manipulate. And that's what we mean by the stimuli materials. They're called stimuli materials, manipulation materials, experimentation materials. It's all the same thing, which are the materials, the visual, the audio that people are going to see in your experiment. So whether it's like movies, video games, images, pictures, music, etc., right? So that's about like the validity of the experiment itself, that the materials represent actually the things you're talking about. You claim that it represents. And then the issue of random assignment is that solve the issue of generalizability from a non-random sample. So even though if you don't have if you have a non-random sample, or if you don't have a random sample, you could still generalize from the experiment because you have random assignment. You remember what random assignment means? What is random assignment? Anyone? So in experiments, do you select which group you're going to join, or that will be selected for you? Remember that?
It's up to the researcher to assign the groups of who's in which one.
That's actually not fully true.
Not on purpose, like choosing between people.
Randomly,
you assign somebody a number and then
yeah. So non-purposefully, you're right. So randomly, yeah. So the participant don't select the group they want to belong to, because as we said, that would invalidate the whole experiment, right? If we say, yeah, you want to see a commercial about taste or a commercial about nutrition, and then you pick, that means you already picked what you like. Okay, so we cannot see the effects of if you're going to like it or not, because we flip, so it has to be randomly assigned. So the researcher randomly, right? So just by a computer, click on this button, and then it would randomly get you to group A or group B or group C, or you would draw something out of a hat or so, But yeah, and so yeah, the researcher does not handpick or cherry pick, and the participant do not select. It's randomly assigned. So that what it means. And so that will take care of the issue of sample to population generalizability, because we want to see if those effects of X on Y, or the independent variable onto the dependent variable, are true. Okay, and because we did not cherry pick how they were assigned, we would say that effects would stay true across different contexts. Okay. And then each issue you want to tackle, the limitations we talked about, would affect other limitation. And so that's what I mean by different experimental design, tackle certain issues, but then come with limitation. So again, if you imagine in video games, right, you want to have as much control as possible over confound variables. But if you try to control all external variables, you're actually then limiting ecological validity. Okay, so if I want to do study effects of video games, to have a complete control, I could design video games from scratch. Okay, and I make everything similar except one thing. But those video games that are created in academic lab do not represent the actual video games people play, right? And maybe you've played educational games before, but they're not sim games. So that would disallow me from generalizing the findings to, and vice versa, right? If I make people play real video games, then I have less control over confound variables. So the challenge is always to find the good balance between those two things, right? So yeah, and those issues, as we said, like confounds, artificiality, and sensitization effect of testing questions. Those are the three major limitations, which you should focus on, by the way, when you're trying to propose your final project and for the final exam. Okay, so that's all I have to say about experiments. Do you have any questions about experiments, experimentation, experimental design, anything? Okay, so now I'm actually going to, so we have time, we have we have actually plenty of time. So I'm going to spend another 15 minutes on different topic, which is statistics. So it's a lot of fun. But so here we go. So let's see here. So this is a sort of, because, okay. Okay, so now I'm going to talk about statistical testing, and it's based off something that I've seen, so in activity number 5 and some of your comments. So I wanted to explain further how we do hypothesis testing, right? So in general, I'm giving an example of how to do an ANOVA. So ANOVA is like t-test, it's a mean comparison but more than 2 groups. So if you have 2 groups, you do 2 tests. If you have more, you do ANOVA. And you want to see if, actually, let me explain why we do mean comparison test. So imagine you're conducting an experiment and you get the results, okay? And in your experiment, your aim is to show that each group would be different, right? That's the point of doing the experiment. In statistics, we start by assuming that all the 3 groups, or 4 or 5 or 6, so 3 here like as a minimum, constitute one similar population, or are the same population, because that's the default position. All right. So to give you an example, to say, for instance, that if you, let's say you're testing the effects of video game type on emotional engagement, and so your hypothesis was saying action game would have the highest emotional engagement, followed by sport games, followed by puzzle games, right? The default position is that all of those groups are similar, because you haven't established your hypothesis yet, right? So the default is we don't know that they're different. So we're just going to assume they are still similar. They're still the same population. So they should exhibit the same characteristics, right? That's the default position. And we call that the null hypothesis, all right? In other words, null hypothesis, all the groups are similar or belong to the same population or represent a similar population. Population here in a statistical sense, by the way, right? So even if they were drawn from the same thing, still population. Then your hypothesis claims that actually, no, those groups are different from one another for the reason that the researcher would explain, right? So you're saying, actually, okay, action game players would be different than sport game players, that would be different than puzzle game players, right? And so, and then you want to demonstrate how they're going to be different. So we call that the alternative hypothesis, okay? The alternative hypothesis is the alternative to the null, and you can have hypothesis 1, hypothesis 2, hypothesis 3, etc., you name it. Like how many hypotheses you want to have, okay? An ANOVA test then would try to compare, like, how would we know then if they belong to the same population or different population? The ANOVA test would then say, okay, if the mean scores, again, the mean score or the average scores, the average values, fall within the confidence interval of one another, then we accept the null. All right, so as to show you right here, let's get me. So you see right here, so this is like how a normal distributed population is, and if there's no difference, so this is the null hypothesis. This is H0. You see here how this is the mean score. Mean score is right here. They all fall within the main confidence interval. So all of these, in other words, are one big population distribution, and those differences right here are just random variation within the same population, right? And then we explain what normal distribution is. So because those differences were small, let's say if they were small, they would fall within one normal distribution. So that means those groups do not represent dissimilar or different groups, but they are all random variations within the sample population. Remember that? Random versus systematic, right? It's okay. So this is showing if the mean scores fall within the confidence interval of one another, that means, yeah, it's one big population group that has no systematic differences between or among them, okay? If the ANOVA test show that the mean score falling outside the confidence intervals, then we reject the null hypothesis. So actually, group 1 is different than group 2, which is and also different than group 3, and or different than group 3. Okay, and this is how it is being represented. So as you can see here, right, and so this is when the null hypothesis is false, so we get a blue. So you see here, this is the mean score, and it's outside the confidence interval of group 2, and same here, mean score of group 3, outside the confidence interval of group 2. So so you see, this is something that is systematically different. It falls, so the mean score of group 3 fall at the extreme end of group 2, right? Remember that, extreme value outliers. So this group could then be claimed represent a different subpopulation, okay? Or a group of the population that is systematically different than the other subpopulation, all right? So that's the logic of hypothesis testing. And remember, it's about, we always say we accept the null and we reject the null, but that doesn't mean we accepted the alternative hypothesis, right? Because they could be multiple alternative hypotheses, as we demonstrated last time, right? So you're just showing here that those are systematically different, but we don't know yet if your hypothesis is the most plausible explanation or not, okay? So this is only about showing if they are statistically similar or statistically dissimilar, okay? Let me show an example of this. So this is like, read it. So this was an experiment, let's say it was by Jones and Coing. It's actually, they are actually from Department of Psychology in University of San Diego. And so they had an experiment with so they had two conditions. You know when you purchase something at the supermarket and then they ask you for charity? Like, could you add, you can add $1 for charity, So they did an experiment online, and so they made you make a purchase, and then would be one purchase would be associated with the social costs. So let's say helping the environment, and one purchase had no social costs associated. Okay, so it's just like a regular product, no saving the environment. And then in a follow-up question, they would ask you, imagine you have a $100 gift card, what percentage you would like to donate to charity, okay? So they had these two conditions: social costs associated with the purchase and no association with social costs, okay? And then the second variable was the gender, right? So the just binary, it was in this experiment, so male and female, which means they would have, so they had gender and they had two conditions. So they will end up with how many groups? It's 2 by 2. 2 by 2 equals, yeah, 4. Thank you, Jennifer. 4. So they would compare 4 groups. So let's see how it goes out. So the dependent variable, okay, as I said, percentages of what percentage of $100 gift card are you going to donate? And so they would say here, there was a significant main effect of gender. On average, so females donated a higher percentage of opportunity to charity than men. Let me read the numbers and tell you which numbers you should pay attention to. I'm not going to explain what F score is, but just in general, this is a standardized score they gave to the mean scores. So because scales have different variables, some scales have 1 to 7, some scales 1 to 100. So F score is a way to standardize all of that. We're not getting into it. But look at the p-value. The p-value is saying p equals 0.02. All right. And so this is for the difference between the two genders. So 0.02 means it fall into the 98th percentile. So if we gonna draw these, let's see right here. So this is so part of my drawing. This is the first group. So imagine this is the 98th percentile. 98th. So the mean, yeah. So the mean score of the other group fall here. All right. So they were here. Actually, this is bad drawing, but so it fell here. Okay. This is where so it fell right here. Okay, so at the 98th percentile, Phil. So it means it's significant at the 95th, the 95%, because it's lower than 0.05. Okay, so may I like to remind you, p-values, depending on how rigid you want the test to be. So you could test at 95%, 98, 99%, or 99.9%, right? So this one here, it's showing that the mean score of group 2 fell outside or right at the 98th percentile of the distribution of the first group. That's what it says in here, okay? And then it gave you the mean score. So for female, it was 48.75. So it's $48.73. It's out of $100, right? And for male, the average score was like almost $44. So the difference was like mere, like what is it? Like $4 and like $5. Like almost $5. Like let's say $5 to make it, to round it up. So $5, right? And so you might think again. So how do you know it's different? So you might think, okay, $5 is not a lot, but it's actually significant. So regardless of what you subjectively think about it, because we showed that the whole distribution is at the extreme value. So the whole distribution of the second group at the extreme value of the first group, then those two subpopulations are different in that characteristic, right? Because if the value of the mean scores were here, okay, it's a random variation within. So we didn't show a systematic difference. But when you compare, yeah, the mean score falling outside the confidence interval, that establish exactly that the two are statistically different, or there's like a statistically significant difference between the two groups, which mean they represent two different subpopulations when it comes to this specific variables, which in this example, charity donation. So this is going to be the last thing. Let me demonstrate that in Jamovi. So we'll do another one. And real quick, I'm going just to show how it looks like, just to make sure that the point is really established. So let's see here. Okay. Where is your movie? Going to be. All right. So this is from the data set I have for activity number 5. Okay. And which you can still download, and you might play with it if you want to test it. And so, you know what? Let me do it from. So we're gonna do ANOVA. Okay. So we'll do one-way ANOVA, and we want to compare. Let's say. So you have a group of variables. So you want to see if what's the effect of income level. Okay. On luxuries purchase frequency. So how many times in a given period of time, like how many times do you conduct or make luxury purchases? Okay, that was the variable. This is from a real data, by the way. Those are not made up. I changed few things so they stay anonymous, but this is from a real data I conducted. Okay, so let us just do this simple test, and then let's here have descriptive table and descriptive plot. Okay. So you see right here, right, that I have the p-value. You see what the p-value is? So it's less than 0.001, which means that the mean score is actually at the 99.99 percentile. So if you could imagine like drawing the 3 groups, the mean score actually second group were at the very last tail end, at the very end of the tail of the first group, and then the third group at the very end of the tail of the second group. Okay, that's what less than 0.001 means. So always the p-value, it's minus 100, right? Because it's a percentage. So if it's at 0.1, that means it's a 99%. If it's 0.001, it's like 99.9%, etc. And here it's showing you the descriptive table. It's showing you the actual mean scores. The income level, so this is from lower to high. So income level 1 is low income and 3 is the highest income. And so the mean score, so this was a scale out of 7. For group 1 was 1.83. For group 2 is 2.06. And for group 3 is like 2.46, okay? And then you look at the plot. And so here, those, you see this blue line, those are the confidence intervals. Okay, so yeah, so the confidence interval is actually this. So right here, and those are the mean scores. And as you could see, the mean score of group 3 fall outside the confidence interval of group 2. And the mean score of group 2 fall outside the confidence interval of group 1. Okay, so that means we cannot claim all of these belong to one group with random variations. But actually, because we compare the distribution of the whole group to the distribution of the other group. And this is the key difference when we have by statistical distance. It doesn't look only at the raw mean score. It's actually compare the mean score with the distribution of a group to the mean score and the distribution of the other group. And so that's why, like, if you find like they talk about statistically significantly different or not different, that's what we mean, right? You could have nominal differences in mean scores, but we cannot tell if they are systematic difference or random differences until we look at the examine distributions as well. That's something I wanted to clarify in terms of like statistics. And I hope that made it more simple. I hope, and I did not confuse you more. So that's it. That's it for the materials of the semester. So Monday, by the way, is going to be an exam review. So it's an open day. If you'd like to show up, you could show up, or not, if you prefer. If you come on Monday, like have questions, you can ask me anything. It will be a full open day. If you have anything about the final group project, also you can ask me. Any last minute questions? Okay. All right, so I hope you enjoyed the semester, and I wish you all the best. So let me know, send me emails, questions, messages, if you have questions about the group project or the final exam, okay? So yeah, take care and goodbye and good luck.
Thank you.
Thank you.
Thank you. Thank you.